Hello and welcome all to the fifth video of the HAPRA and VHDL playlist. I'm Sanad once again, and in today's video, we are going to implement what we learned in the previous 4 videos and test our knowledge out. We will not be introducing new concepts rather than only using the knowledge we have gathered. This video is a really important part of our progress in VHDL. So in case you didn't understand a section from this video, kindly repeat it or search for online sources to further better your understanding and knowledge of the VHDL and the HAPRA module. Our goals for today is to write our own VHDL project from scratch. We will first generate our own propositional formula and solve its corresponding truth table. We will then draw the integrated circuits for our formula using the IEC 60617-12 norm and implement the circuit from scratch in VHDL. We will then, last but not least, we will then implement the test bench for our design, and finally we will generate a waveform from our design and then analyze it. In total, there are a maximum of 6 steps for each VHDL program. I advise you all to follow a similar plan when trying to implement anything in VHDL, as it is a well-constructed and coherent plan that will ease the way for you. The first step of our journey in today's video will be to generate a propositional formula. This can be anything and everything. It doesn't have to reflect any functionality at all. I just used this example to cover all the material we went through in the previous video. In our case, what I want to implement in VHDL happens to be the formula right in front of you. So basically, we have A or B, and the result from A or B with the result of not C is then used with an AND gate, and the result of an AND gate is then XORed with our 4th variable, and that is the D. So basically in this example, we have 1, 2, 3, and 4 variables, and we have 1, 2, and 3, and 4 gates. You will now get a better idea when we analyze it a bit further using a truth table. The second step of the process is to solve the corresponding truth table of our formula. So basically, we have A or B. The answer of A or B together, in this case, for example, is 0. The 0 and not C, so not C is 1, and 0 and 1 is then 0 XOR D. So D in our case is 0. 0 XOR 0 gives us the output of A0. Similarly, when we have a 0 or 0, so A or B gives us a 0, and not C, the C is a 1, so 0 and 1 gives us a 0, XOR D, because our D has the value of 1, so 0 XOR 1 gives us the output of a 1. These are 2 examples of how to solve the truth table for our formula. I left a few spaces untouched, the parts marked in red. Please pause the video for a second and try to figure out the solutions for the 4 spaces I left out. So pause the video and return in a bit. Hopefully you have paused the video and tried it out on your own. We'll now look at the solutions. In this case right here, you should get A1. So basically 0 or A1 gives us a 1, and not C. Not C is a 1. So 1 and 1 gives us a 1. 1 XOR D, which is a 0, or a 0, sorry, gives us a 1. Similarly, this example should also give you a 1, while this a 0, and the final one should also give you a 1 or a higher. The answers you should get are 1, 1, 0, 1, respectively. We will now need to draw the integrated circuit using the IEC 60617-12 norm. I will provide you with a link in the description. It's the same link shown on this slide right here, which shows you the basic gates and how they should be drawn using this norm right here. I will now open the link for you to show you what I mean. This is the link I provided to you in the description and on the slide. So basically, an AND gate is drawn like this right here. It of course can have multiple inputs and not just two, but should only have one output and has an AND sign right in the middle of a box. An OR similarly is drawn using the greater than or equal sign followed by a 1, has two inputs or more, but only one output. The NOT is drawn by drawing a box, and in the middle you should write a 1 followed by this circle right here, which basically tells us that it's a NOT. An AND or a NAND is a basic AND followed by a NOT circle. Similarly, you can check out all other examples in this link. You have the NOR or NOR, the exclusive OR, XOR, the XNOR, the exclusive NOT OR. You also have the RS flip-flop made from NOR, the RS flip-flop from NAND, D flip-flop, T flip-flop, and RS flip-flop, and finally the JK master flip-flop. You will need to use these in the HAPRA module, so I advise you to check out the link on your own. We will now return to our presentation and try to draw the integrated circuits using the images in front of us. Okay, let's start. So we will first draw this right here, and we can do that by first writing all of our variables. So we have an A, a B, a C, and a D. Firstly, the A is used with an OR gate with a B. So basically we have the two lines coming from the A and the B going into an OR gate, and the output, let's call it A1, is the output of the OR between the A and the B. Similarly, we have a NOT C. Let me just change the color. We have a NOT C. The C goes into the NOT gate of the IEC norm and comes out as, let's say, 2. And then finally, or not finally, last but not least, we have this phrase right here. So the first 1 and 2 is together used with an AND gate. So the input from the output of A or B and the input from the output of the NOT C is used as an input for the AND gate, and we have a 3 coming out, let's say. And finally, we have to use all of this with the XOR D, and let's call it a 4. And yeah, this is a 3. So basically, D XOR number 3 gives us the out. Let's test it out. So basically, if A is equal to 1, B is equal to 0, C is equal to 0, let's say, and D is equal to 0. We should get the output of 1. Let's see if our integrated circuit is drawn correctly. So basically, a 1 comes here and a 0 comes here. 1 and C takes the value of a 0, while the D takes the value of also a 0. So 1 or 0 gives us a 1. And then 0 not gives us also a 1. 1 and 1 gives us a 1. And finally, 1 XOR 0 gives us the answer of 1. And this is how we know that our drawn integrated circuit is done correctly. We will now implement the circuit from scratch in Vhdl, and then implement a test bench for our design, and finally generate a waveform from our design and analyze it. We will be doing these 3 steps separately from the PowerPoint, as I will show you everything hands-on. So I will now open Notepad++ and start with the implementation of the design. We will first start by creating a new folder. Let's call it a random project, random Vhdl project. This folder has the AND gate files from the last videos. So we will move the AND gate from this folder to this video folder to use it in our component, in our design, since as you can see in the picture on the right, we use a normal AND gate. We will also need, I can show you what this has. So basically this has the AND gate logic that we discussed in the previous videos. We won't need any test benches of the components inside of our design. What we will need is a separate test bench for our design as a whole. So basically what we will also need is the OR gate, the NOT gate, and the XOR gate. I won't be able to show you these kinds of solutions, as you will be responsible for doing so in your OpenGAM. I will just move them to our folder. So basically we have the NOT gate, the OR gate, and the XOR gate. So now we have the AND gate, the NOT gate, the OR gate, and the XOR gate. And what we will do now is we can close the folder right here, and we open Notepad++. We start a new project, and let's copy and paste the library IEEE. And once again, I forgot to change the language into Vhdl. Let me just make the screen a bit bigger now. Okay. So let's start with doing the entity declaration of our design. Let's do entity random. Let's call it random is. And then we do the port, which takes, as you can see here, 4 inputs and 1 output. So we'll do A in std logic. We can copy and paste this 4 times. And the 5th time for the output. So we have an A, a B, a C, a D, and finally the out. Let's call it output, since out is a reserved VHDL word, and we will change its mode into an out. We will then close the port, and we end the entity declaration part. What we'll now need to do is write the architecture declaration of our project. So architecture, let's call it random logic of our entity, which is called random is. And what we will now need to do is instantiate the components we are going, the subcomponents we are going to use, in addition to the signals we are going to use as well. So basically, as you can see here, we need the AND gate, the OR gate, the NOT gate, and the XOR gate. Let me see what they're actually called in our projects. Okay, AND gate, NOT gate, OR gate, XOR gate. Okay, so what we will now need to do is call our components. So we have the component AND gate, the first component. We also need to write up its port. I used the false. Yeah. What we need to do right now is also use the same ports of our AND gate from the AND gate design. So as you guys recall, we have input 1, and it is an NSTD logic. We also have input 2. It is also an NSTD logic. We also have an and output, which is the out STD logic. We end our port map, and we finally end our component. We will also need the NOT, the OR, and the XOR components. So we paste these 3 times. And we can call this the, as it's called in your file, this is the OR gate. This is, let's say, let's start with the OR gate. It also takes input 1, input 2, and gives out OR result. And we have another component, which is the XOR gate. And in the XOR gate, we have the port names for the XOR gate, input 1, input 2, and XOR result. We finally have the NOT gate component, which we also should instantiate. So let's call this NOT gate, which takes only 1 input and 1 output. This is called the NOT result. In our port name of the NOT gate in the implemented code, there's something wrong I wrote, which I forgot that the last port shouldn't have a semicolon at the end. So we did this and this and this. And then, okay, perfect. And now we need to instantiate the signals which we are going to use for our design. So basically, we have, we will need to use 4 wires or 4 signals. I'll show you why. So basically, this is the first signal we are going to need. This is the second signal we are going to need. the third signal we are going to need, and finally the output is the fourth signal we are going to need. So we instantiate, let's call them wire 1 from type std logic. Please note that, as we have discussed in previous videos, the signals don't have any modes. They don't have any in or out. So we call this wire 2, wire 3, and wire 4. And finally, we begin our body. What we do, what we need to do now is that we need to implement the design shown on the left side of the screen. So we will first implement the NOT gate, since it's the easiest to implement, and then you'll understand what's gonna happen. So what we need to do is, as I showed you in the previous videos, how to use a port map. A port map calls an instance of the component we need. So we can call that random 1, or let's make it more clear, NOT instance is its name, and we call the NOT gate port map. And what we need to do is, the NOT gate has input 1 as an in. So we write input 1 and takes the value of C. NOT gate takes the value of a C. As you can see in the left side of the screen, C is an input for our NOT gate. So input 1 takes the value of a C. Let's now continue. The output result of input 1 is going to be one of the wires. Let's use the wire 1. So NOT result will take the value, or will give its output to the signal wire 1. Since again, the signals can be used both as inputs or outputs. Let's now do the OR gate, which takes both inputs A and B as an input. So let's call it OR instance. And uses the OR gate port map. The OR gate, as you can see here, has 2 inputs and 1 output. So we have input 1 takes the value of A, and input 2 takes the value of B, while the OR result will give its value to the second wire shown on your left screen, which is this, which is the second signal. So we will give its value to wire 2. We will need also an instance of the AND gate right here. We will need an instance of the AND gate, and takes the values as inputs, which is wire 1 and wire 2. Sorry, vice versa. Wire 1 and wire 2 will be inputs for our AND gate. Since, once again, I want to re-emphasize that signals can be used both as inputs and as outputs. So we will need an AND instance. Let's call it an AND instance. Uses the AND gate port map and has 2 inputs. Input 1 takes the value of wire 1 or 2, doesn't matter, and input 2 takes the value of wire 2. And we have the AND output, which gives its value to our third signal, which is wire 3. Finally, The last component instance we are going to need is the XOR component. So we can call this, and by the way, the XOR component similarly takes the signal value of wire 3 and D as 2 inputs and gives its output to the wire 4, which we have done. Okay, so I can leave that. I need to erase this. So we basically need an XOR instance. Let's call it. It will use the XOR gate, uses a port map. The XOR gate has input 1, takes the value of wire 3, and input 2 will take the value of a D. And finally, the XOR result from our output of the component gives its result to wire 4. So when I highlight on one word, you can see that this NOT result inside of the NOT gate component is the same one you used in the port map. Similarly, if we press on the XOR result from the XOR gate, it's the same one we used in the port map, and so on. Wire 1 is used both in the NOT gate and the AND gate. Wire 2 is used in both the OR gate and the AND gate, and wire 4 is our output. And finally, wire 3 is both used in AND gate and the XOR gate, as shown in the left screen side of our design using the IEC norm. There is one last thing we need to do right now, and that is the output of our main design, which is the random entity declaration part. We have an output, so we finally give output the value of wire 4. Let me note that this sign right here acts both as an input and an output in the port map. So basically here, wire 3 is an input for input 1, D is an input for input 2, and the XOR result gives its value, which is an output to wire 4. But outside of a port map, the signal assignments should always follow this, what you see right in front of you. So output takes the value of wire 4. And finally, what we need to do is we end our architecture declaration we called random logic. As you can see, it's called random logic, and we end random logic. This is the whole code. We will now need to implement the test bench. Let's first save this, save as. Let's call it, it should be called the same, guys. Please note that the name should be called the same as the entity. So we call it random. And we make sure it is a VHDL file. So SIC hardware description language file, save, and it's now saved. Now to implement the VHDL test bench, what we need to do first is change the language and make sure it is a VHDL language. And firstly, we will copy and paste the library IEEE from our random, since it always has to be available in all VHDL programs. We will have an entity declaration which has no inputs or outputs. We can call our test bench random _ TB is, and finally end the entity declaration part without any input or output ports. As we have discussed in the previous videos, the entity declaration in a test bench has no inputs or outputs. As for the architecture declaration, most of the work is going to be in it. We can call this architecture declaration test, or actually random, or let's call it test. of the entity declaration is, and inside of our architecture declaration, we need to call, as we have discussed in previous videos, on the component we want to test. So basically we have one component, and we won't need to call on the AND, XOR, or OR gates, not gates. We don't need them in the test bench. We only need to call the main component, and that is going to be the random itself. And we have to get the ports. We can actually copy and paste the ports from here. So we basically copy and paste the ports, and perfect. So, and finally we end the component. Now what we need to do is we need to call on or instantiate some signals. We can call them the same names as available in the ports. Let me just fix this right here so it's more clear. So we can call them signal A, B, C, D, and output. And the signals, once again, have no mode. They only have a type, which is going to be the same type shown on the ports. And we begin our body, architecture body. Once we do that, we need to call on a port map or create an instance of the random component. We can call that random instance or random underscore instance. And we use the component random port map, and we give A to A, B to B, C to C, and D to D, and finally the output to the output. And we end our port map. Now we need to start a process. So we call a process begin to give it the stimuli or inputs for the signals. Note that this output right here is the same as this one, while this output is the same as this one. You will understand it more a bit when we write the stimuli or inputs for the signals. So basically we need to give the values. We can give A the value of 0, for example, B also the value of 0, C the value of 0, and D the value of 0 as well. Then we can wait for 10 nanoseconds, 15 nanoseconds, doesn't matter, your choice, but in my opinion 10 nanoseconds makes the most sense. We can then copy and paste the following as many times as we want, depending on how many values or tests we need or want. So we can change the A the first time, we can give it, we can make the D as a 1. So it will give us a true, since it's as we have discussed. We can change the second time the A to a 1 and the D remains to a 0, and finally the B to a 1 and D to 1. So basically the output of our program should be 0, 1, 1, and 0. Okay, what we need to do now is finally wait one last time, and we end our process. And we finally end the architecture test by using the reserved word and followed by the architecture declaration name. We save it, and we need to call it the same as the entity declaration part, random TB, random underscore TB. Make sure it's a VHDL file, and we save. What we need to do now is we can actually close this right here. And what we need to do now is we need to open a terminal. And we need to compile all of the subcomponents inside of the random itself, and the random to be. So what we do is ghdl -a and gate. And gate dot vhdl. And we need to do the same for the OR gate, the same for the XOR gate, the same for the NOT gate, and finally the same for our random file. And finally, and by the way, it doesn't matter if you use VHDL or VHD, it's the same thing. It's the naming. Random and random TB were saved as a point VHD, but the other source codes were saved as point VHDL. So you need to keep that in mind, since if we write point VHDL, it's going to give me an error, and that's why I use point VHD. You need to follow the naming system or what your file is actually named. And finally, we need to analyze the last one. As you can see here, we have some errors. We can open and check out the errors ourselves. It's actually good that some errors appeared, so I can show you how to know where the errors are. You can see it's shown in line 23. So D takes the input of a D, and output takes the input of output. Seems to be the case that I forgot to complete this port map. We save and we finally compile once again, and as you can see, we have no errors. And finally, I will use a script to run all of the commands needed to open Gatica Wave. We discussed already these commands in the previous videos. I only use the script, and in the Übungen, you are going to develop your own script. That's why I'm not going to show you mine. Anyways, when I press on enter, it should open Gatica Wave and show all of the signals A, B, C, D, and output. But there seems to be a problem. So let me figure out what the problem is, and I'll come back right to you. So basically, I figured out what the problem was. I used an OR gate with 4 inputs, and in our random.vhd file, in line 50, we only have input 1, input 2, and in the OR gate itself, we also have only input 1 and input 2. But we can fix that. Sorry, I can't show you the answer. We can fix that by just deleting the following. So we save it once again, and we close this, and we close this as well. And we can close Gatica Wave as well, once again. And we close this as well. And finally, we need to analyze the OR gate once again. No declaration for input 3. I must have forgot to also remove the input 3 and input 4 from the architecture declaration. Let me just pause the video. Or actually, it doesn't matter. You can see the answer. It's not that bad. So as you can see, this was the problem. So I remove these, and we can save it once again. And finally, we analyze one last time, and we analyze the random once again, and finally we run Gatica Wave. As you can see, there are no errors appearing on the screen, and that's why this should also work, no problem. And we paste the output, and finally, as you can see, we got the answer we expected. We got a 0, 1, 0, 0. So basically, when A, B, C, D were 0, the output is also 0. But when A, B, C were 0 and D was 1, the output was 1, since there's an XOR at the end of our expression. And finally, it stayed high since A is 0 and all other values are 0. And this way, we also get a 1. And finally, it went back to a low. And because A and B and C were a 1 and D was a 1, and so 1 XOR 1 is a 0, and that's why it showed a 0 finally. Maybe to analyze your program better, you can change the color format of your output to another color, for example, an orange color. This way, maybe you can understand the code a little, the waveform or wave function a little bit better. As for everything else, this wraps up our video for today. I hope you have benefited from this lecture. I advise you all as homework to implement the same steps we learned today to come up with a formula on your own and try the process on your own. It will really help you learn a little bit more Vhdl and become a little bit more used to the let's say the process of writing a Vhdl program. Do not hesitate to send me what you do on my email. I will gladly respond to each and every one of you and offer a hand of help. I thank you all for your attention, and this is Sanad once again, and until next time.